Um, Assalamualaikum warahmatullahi wabarakatuh. My name is Fauziyyah Marwa with the student number of 22068-21510. And in this presentation, I'm going to talk about rheology of polymer. So basically, the reason why I talk about this is that if we were talking about polymer and how the properties actually occurred. Um, if you're, for example, you're giving a stress or you're giving a heat, there will be something called melt-processing, which the polymer will eventually become melting when the temperature is too high. And from that, usually in the industry, you could add solvent or add functional groups that makes it maybe more dense or have more viscosity, and or it could be talking about the flexibility or the ability to resist deformation. Now, in the melt state, there usually often something called viscosity, which we're going to talk about in this segment. So viscosity usually, if we're talking about, for example, like water have viscosity or something like honey, but both of them actually has different viscosity. We could look maybe from its density or its molecule, but usually larger viscosity means more dense and have more molecular weight also and more interaction between molecules. And since there are a lot of more example rather than just water or maybe oil, there's something on the example on the fluids, which this is the content. What I'm going to talk is non-Newtonian fluids. So introduction, the Newtonian fluids definitely doesn't follow the same rules as the usual fluids. They have a variable viscosity, means that their thickness can change depending on the amount of force. So, okay, something like water or oil is included in Newtonian fluid. So if we're looking at a graph, viscosity and shear rate, it does nothing. It's basically just a straight line, which means that if you want to give any force or anything, it will stay the same. Well, there are also other three types, which is Bingham plastic, dilatant, and pseudoplastic. So basically, for Bingham plastic, it will be the more you give forces, the viscosity actually become less. It's kind of the same with pseudoplastic, but very low viscosity rather than Bingham plastic at the start. And if we're talking about dilatant, the more you give shear rate, then it have more viscosity. So there are types which is shear thinning and shear thickening. Shear thinning is a tendency of some material to decrease in viscosity when driven to flow at high shear rates, while shear thickening, which increase in viscosity when driven to flow and high shear rate. So more shear rate, more viscosity is shear thickening, while more shear rate and less viscosity is shear thinning. So we're talking, okay. So soda plastic, just this one, is the example is tomato ketchup. When you're giving force to tomato ketchup, it'll be have less viscosity. And then dilatant, when you're giving more shear to oat black or cornstarch water, it will be have more viscosity. And for Birmingham plastic fluids like toothpaste, very same with soda plastic, but from the start point, it has lot more viscosity than tomato ketchup. So next I'm going to talk about melt flow index and why is it important. For melt flow index, in polymer, it's to determine how easy a thermoplastic material flow. So it's basically to measure the material's melt viscosity. So melt flow index count by weight of the test in a gram per 10 minutes. So to do the practical work to the lab, you need to heat the polymer, and normal load will be applied to the molten material, and then it will be extruded in for over 10-minute period and will be recorded as MFI. So we're going to talk about the effect of molecular weight to viscosity. So, as molecular weight of polymer increases, the chain become longer because more molecular weight equals to longer chain of polymer, and it's also have a greater chance of them becoming entangled to each other. So this entanglement act like physical junction and will be restricting the movement, which is make it become even stronger. And the more entanglement present, the higher the resistance to flow, resulting in a higher viscosity. From higher viscosity, you will get higher strength, which I already talked about, higher impact strength, because of lower degree of crystallization, higher chemical resistance, and reduction of the fluidity, which is basically if you ever seen a fluid, maybe slime, it's like the fluid becomes much more slower because it's become denser, something like that. And in here, if you can see the more, okay, so the blue one is low shear rate, while the yellow one is high shear rate. So in low shear rate, the entanglement dominate, right? The long entangled chains are sluggish and resist flow, resulting in a high viscosity. So low shear rate means low force, and low force mean more more entanglement, because if you give more force to the polymer, the entanglement will basically break it down. So definitely more shear rate means more force. As you can read in here, as the shear rate increases, the applied force started to play a role, and then partially disentangle some of the chains, allowing them to flow more easily. And this is called shear thinning. But definitely in shear thickening, it will be works completely opposite. But since we're talking about polymer, we're going to talk about shear thinning. So that's how it works. So next, we're going to talk about the effect of PDI to polymer viscosity. So this should be the graph. But basically, how PDI affect the shear rate. There are narrow PDI and broad PDI, and narrow PDI are the polymer chains are relatively uniform, while broad PDI has a wide distribution of molecular weight, which means they're longer chain and shorter chain. So PDI definitely are in lower viscosity because the flow is less hindered by chain entanglement and the viscosity decreases uniformly with increasing shear rate as the chain are similar in size. While broad PDI with much more variation of chain the long the chain, it will goes into the higher viscosity because it has more entanglement and increasing resistance flow. And the presence of the range of chains means that as shear rate increases, the smaller chain will align and disentangle more quickly, leading to non-uniform decrease in viscosity. Next, I'm going to talk about the effect of additive. I don't think, okay, now here it is. This is for the graph for the earlier. So there are a lot of additives on polymer, but this is just a few of them. So first is fillers. If you're using injection molding or something, if you want to put the plastic into a not container, but you know what I mean, it's to the shapers, to the mold. It needs to be filled really, really densely. So sometimes it won't fill 100%. That's why you need to use fillers to enhance their mechanical properties to make it more not as stiff and to increase the viscosity by disrupting the flow of the polymer and making it more difficult for them to slide past each other. Yeah, I think it should be enhance their stiffness. Sorry, it so it gave it more strength basically. Next is plasticizers in PVC is to reduce the viscosity by increasing the free falling between polymer change. So it's definitely to make them more flexible and more easier to process. Thickeners in paints, to increase the viscosity, so the paints will stick to the wall more and to achieve that desired consistency and flow behavior. Last one is lubricant, is to reduce the friction between polymer chains and allow them to slide past each other more easily. So the real world examples is polyethylene. So there are two types of polyethylene, which is LDPE and HDPE. There are not always the same types of numbers of MFI, but from what I got is the LDPE has an MFI of 0.5 gram per 10 minutes, while HDPE has large amount of 10 grams per 10 minutes. So there this video. You can watch it on YouTube, but a DPE usually used for high strength and stiffness for packaging materials, while HDPE used for pipes and container where you need more stiffness and more viscosity. So next is polypropylene. Yeah, there should be bottle caps here, but you use basically this for using bloom molding and extrusion. Usually used for bottle caps. And I think we'll probably also use for fabric, if I'm not wrong. Next is polycarbonate. Also use injection molding. You can watch it on YouTube. For example, is the windows. Oh, actually, okay. yeah, you could watch it. But yeah, that's all, I guess. I hope you learned something about the rheology of polymers. Sorry if I have any mistakes. Wassalamualaikum warahmatullahi wabarakatuh.